Good morning, physics class. We got video 3 here talking about circular motion. We've talked about circular acceleration and circular velocity and kind of how to work those two out with our new formulas over here. We're going to be looking at, for this video, a lot about force. And again, force is just mass times acceleration, and that's exactly what tension is as well. We're going to look at tension a lot today as well, in the sense of basically the tension of the string, how much force is on the string when something is in motion or when something is hanging there. And so this video will kind of focus on that. So question 5, 6, and 7 from the practice sheet we'll be looking at today to really kind of focus on the theory and trying to understand what's happening in this circular motion. So let's get at it. We're going to go to question 5 first. Okay, let's throw it up there. All right, so we've gone through a little bit about tension, but it's always been with horizontal circular motion. So it's always been with kind of like our horizontal side to side. I can do it this way as well, I guess. There we go. So it's always been like horizontal, which is more side to side. In these next videos, we're going to be talking a lot more about our vertical, which means like going up and down. Okay, and there's quite a bit of difference because horizontally we kind of ignore the force of gravity on the ball because it's going like side to side, so gravity is not affecting it positively or negatively. When I have a vertical, gravity is going to be helping it on the way down and hurting it on the way up in a sense, but it's actually a little different for tension. When the ball is going down, there's more tension on the ball because it wants to go faster and there's more acceleration going down. When the ball is going up, the ball is slowing down, there's less acceleration, which means there's less tension in the ball. Because eventually if I slow down enough, it's going to just fall, which means there's no tension on the ball at all. So let's try and make sense of that for question 5 here. It says a body mass of 3 kilograms is whirled to the end of a string kind of like mine with a radius of 1.5 meters. 1.5 meters at a constant speed of 20 meters per second. That is a fast speed. Okay? Find the tension of the string when A, the body is like the ball's at the lowest point, and then when the ball is kind of at the top of the point. Let's first find acceleration, because again, for tension, it's just a force. It equals force, which means it equals mass times acceleration. Okay? Now this can be split into 2 parts. Acceleration can be first from force of gravity, and then second from force of like the circular acceleration. So force by like the circular acceleration. Okay? So let's kind of look at this. First, let's find our acceleration just from the velocity here, because we can do that. So acceleration equals v squared over r, which means 20 squared over 1.5, and I get 266 meters per second squared, okay, which is very fast. This thing is moving very quick. Remember in the last video I talked about how acceleration can be quite drastically different from the velocity when we talk about like circular motion. That's because it's always changing direction, which means that acceleration actually gets very, very high sometimes. So that's correct. I know it just seems odd from a lot of the work that we've done, but that's how it is for some circular motion. Okay, so let's not try to think about this. If this was now horizontal, if this thing was just going horizontally, all I'd have to do is just go this acceleration times mass, and I'm done. Because this thing is going vertically, let's try and draw this out. When the ball is going down, it says when the body is at its lowest point. So I'm going to draw a circle here. When the ball, and so here's the string, here's our radius. When the string is straight down, and there's a ball there, okay, first off you have your acceleration of 266, okay? But when the ball's at the bottom, when it's going down, like when the ball is heading this direction, like our acceleration because of gravity is also going down. Okay, it's also going down because again, if I have something that's going like this, holding like this, gravity is pulling it down with a force as well. And so when the ball is at that lowest point, the acceleration of gravity is also going to be there. So you can do 2 things here. Either you can just add the acceleration to the acceleration you already have, or just add the forces together. I'm going to add the forces together. So I'm going to have 2 forces here. I have, for part A, I have force of gravity plus force of my actual like centripetal acceleration. I put a C there for like circular motion, for the circular acceleration. So force of gravity, I'm going to go just my simple mass times gravity. So just 3 times 9.8. So when I go 3 times 9.8, I get 29.4 plus the 266 times 3, which is the big number. 798. So I add those together, plus 29.4, and I get 827 newtons. For B, when the ball is actually at the top point, so when it's up here, okay, gravity is actually wanting to push the ball down, which means the string is actually going to have to do a little less work. If you go slow enough, you'll be able to tell that the string actually does more, like it feels like it's like tighter at the bottom. And that's because, again, gravity is making the string do less work at the top and more at the bottom. So for B, what we're going to do is we're going to take our force of gravity minus our force from our actual centripetal acceleration. So basically it just ends up being 29.4 minus 798. Now this won't be negative. You'd rather go 798 minus 29.4 because there's not negative tension. Tension is kind of an absolute value. You're not going to have negative tension. If there's negative tension, just means there's no tension at all. That the string has to do no work. You can't have negative tension. So it's kind of like an absolute value here. So when I go 798 minus 29.4, I get an answer of, what do I get? 768. 768 units. Okay, so there's just a little theory understanding that when we have a circular motion, the tension is going to be different if it's vertical. It's going to be lower, like more at the bottom, less at the top. Okay, the next two questions are going to kind of touch on this as well. All right, there's question 5. Question 6. Okay, we have a bicycle rider. Okay, so they're going over some kind of hump. So I'm not going to try and draw a bicycle rider. We're just going to put someone there. Why not? Okay. All right, that's as best as I'm going to try and draw this bicycle. But they're going over this hump, okay, in a circular thing. So they have a mass of 70, a radius of 5, and the speed of velocity of 5 meters per second. You notice how we use speed a lot here because when we use velocity, technically there's a direction. I don't want to keep saying there's a direction because technically it's changing a lot, so we use speed a lot more when we talk about circular motion. Find the force which the seat exerts on the cyclist, okay, as the bicycle reaches the top of the hump. So as it goes up. So if, like, this is kind of like a force normal kind of situation, okay? In the sense of, like, if I'm standing on the ground, okay, the mass times gravity, that's the force of gravity, and the force normal has to do the same thing. If I'm on a bike, okay, if I'm on a bike and just on a flat piece, what does the bicycle, like, have to do to hold me up? Well, it has to do exactly the same as force of gravity. So when we're on flat ground, our force of gravity is going to equal kind of like force normal of bike. Now, when we're going actually over a hump, the bike actually has to do less, sort of like the seat is going to do less force on you, because when you're going around this circle, again, there's going to be an outward force pushed on you. Okay, and that outward force pushed on you is going to, like, kind of negate force of gravity pushing down. Okay, so what would the force of gravity be pushing down normally? So let's just figure that out. We have 70 times our mass. Sorry, 70 times 9.8. That's gravity. So normally, we have 70 times 9.8. This is gravity pushing down you at all times. So there's 686 newtons pushing down if you're on the bike on a flat piece no matter what. Let's actually find the force that pushes out on this because of this, okay? Let's actually find the, like, circular force that's pushing out, the centripetal force there, okay? So let's now see what we got. So we have to find an acceleration first. So let's get our acceleration. Acceleration equals v squared over r, so 5 squared over 5. And so you can notice if you have 5 squared, that's 25 divided by 5, so I have an acceleration of 5 still. 5 meters per second squared. And so now I can just figure out what the actual force circular is going to be. And again, that's me pushing up. Okay? It wants to keep pushing outwards because it wants to stay in its exact, again, directional path. So that force is going to be pushing upwards. All right, so when I do that, my force circular is going to be 5 times 70, which equals, what do I got? 350? 350. and that is me pushing upwards. So gravity is pushing downwards. This force is pushing upwards, which means that I'm going to minus the 2, and that's how much force you actually feel by the bicycle seat now. That's how much work, that's how much force the bicycle seat has to kind of do on you. It's kind of like that force normal situation. All right, so to get the answer for A, I'm going to go 686 minus 350, and I get an answer of, what do I get? An answer of, where is it? 336? 336. 336 newtons. All right. For B, I don't have a lot of room there, so I'm probably going to erase some of this. It says, if the same rider experiences no force from the seat he passes over, find the speed at which he's just traveling. Which means, so basically, again, force of gravity is always going to be putting 686 downwards. If I want to feel no force from my seat, that means the upward force has to be also 686. Okay? So I'm going to kind of erase a little of this right now. So again, force gravity equals 686, which means my force centripetal also has to equal 686. Okay? Which means if I just kind of work backwards, force centripetal equals mass times acceleration, which means 686 equals 70 times A. And so when I do that, I get an acceleration of 9.8. Surprise, surprise, surprise. I just have to basically cancel out the acceleration of gravity. And now that I have that acceleration, I can go back and I can find my velocity. Okay? I'm just going to use this exact formula. The acceleration equals v squared over r. I'm going to plug in 9.8 there, so let's plug that in. So 9.8 equals, my radius is 5, and I have v squared. I don't know what r there is 5. So I'm going to multiply those and then just square root it to get my velocity. And when you do that for B, I believe you get an answer of 7 meters per second. 7 meters per second is the velocity. So if you had a velocity of 7 meters per second going over this hump, basically you actually feel like the force of the seat, like the actual seat on you, because that force pushing upwards is exactly the same as the force pushing down. All right, hopefully that makes a little sense. This one can be a little tough sometimes to understand, but that's okay. Last one, let's go to question 7, the Tarzan question. Most people understand the Tarzan one a little more than this one, but let's kind of go through it. All right, question 7. Tarzan is swinging, okay? Swinging on a vine that will break if the force exceeds, and again, I hate this when I make this. It should be 10 to the 3, and this should be 10 to the 2. If the length of the vine, so the radius is going to be 5 meters. So basically we have, like, again, Tarzan on a vine. Okay, hold it on. I guess you should hold on with a hand. Okay, there's Tarzan swinging this way. It says that the force maximum can be 2,000. Okay, that's the maximum tension, max. Otherwise it's going to break. It says, what is the highest speed he can travel while swinging on this vine? Okay, well, again, if he's swinging upwards, there's going to be less tension. If he's swinging downwards, there's going to be more tension. Okay, so let's just kind of find, again, what's the max speed he can be going downwards. That's usually what you're swinging on a vine for. Not that I've done a lot of that lately, but again, there's going to be two forces. There's going to be the force of gravity, and there's going to be the force of the circular actual acceleration. Let's find the force of gravity first, which is all I have to do is just go mass times gravity. So 100 kilograms times 9.8. So there's already 980 newtons when he's just at the bottom. If he was just hanging there, okay, at the bottom, there would already be 980 newtons on him, which means the max of the force circular can do is 2,000 minus 980, which is 1,020. Okay, so that force can be exactly 920. So now we can work backwards. What is the acceleration that he can have circular, and then what is the velocity he can have circular? So we know that the force can be 1020, which equals the mass times acceleration. So there's the mass, divide mass, cancel out, divide mass. So my acceleration can be 10.2. And then again, I'm just going to put that into my acceleration formula. Acceleration equals v squared over r. I know my R is 5. I know my acceleration is 10.2, 2, and 5. So again, 10.2 times 5, square root. The maximum velocity that Tarzan can go is 7.1 meters. 7.1 meters per second. Okay? So just understanding these forces, when you have a vertical circular motion, that tension is going to be different at the bottom and the top, and to understand that there's usually two forces acting on it. There's the force of gravity, which is just the person hanging on it, and then there's the force of the actual acceleration going like up and down, okay? And so how to kind of work with these forces. Hopefully that made sense. Our next video is going to kind of talk about some angled corners and some vehicles going around, some like circular motions, but with some angles, and kind of how we can kind of work that out with like understanding our dynamics with circular motion. So talking about force parallel as well as force of friction a little bit. All right, class, thanks so much. I shall see you in a little bit. Thanks.